Hi, my name is Austin Cox, and this is Homework 3, Part A1. And we're going to be starting from the first law of thermodynamics, and then we're going to derive expressions for the amount of heat to be added or removed for the isothermal reversible expansion / compression of an ideal gas. So here, we can start with the change of internal energy is equal to the change of the amount of heat that was brought into the system, and then plus the differential amount of work done onto a system. So we can start with going ahead and drawing our system, and it is going to have some force being done onto the system for our work. And this is going to be, the differential amount of work is going to be defined as the external pressure times the cross-sectional area, and then it's going to be times some change in distance, and we can denote that as dx. And then we can further denote the differential amount of work as the pressure external times the differential amount of volume. And in this scenario, our volume is reduced, so that is making our work negative. So now we can rewrite this equation as du, the differential amount of internal energy, is equal to the differential amount of heat added or removed, and then it's going to be subtracted the differential amount of work, which we found to be the pressure external times the differential amount of volume. So now we know that in a reversible process that we do not want work done on the system, and we do not want the work to accelerate. So we can denote our pressure external is equal to the pressure of the system. So now we don't need to have pressure external, we can just have pressure. So we can rewrite this as the differential amount of internal energy is equal to the differential amount of heat added or removed reversibly minus pressure times the differential amount of volume. Because we know that this is an ideal gas, we can set the pressure internal is equal to RT over V. And then we know that du is a proxy for temperature because it only depends on temperature. And we have a constant volume heat capacity in this scenario. So now we can denote this as CV dt, differential amount of temperature, is equal to the dq, differential amount of heat reversible, minus, and then we can rewrite P dV as RT over V dV. So we know that the constant volume heat capacity will go to 0 for this scenario. So moving forward, we can write that the differential amount of heat added or removed reversibly is equal to RT over V dV. And to further evaluate this, to further derive this expression, we can integrate both sides. And on the left side here for our dq reversible, we can integrate from 0 to the amount of heat needed reversibly, q rev. And on the right side, we are going to integrate from our first volume to our second volume. So then now we can go ahead and integrate, and this gives us q rev is equal to, And we have RT, those are constants. RT times the natural log of V2 over V1. And there you have it. That is the expression derived from the first law of thermodynamics for the amount of heat added or removed in a isothermal reversible expansion or compression. Hi, this is homework 3, part A2, and here we are going to derive the pressure volume and the pressure temperature relationships associated with the adiabatic reversible expansion or compression of an ideal gas. And we know that adiabatic means perfect insulation, and that allows for there to be no transfer of heat. And from the previous part, we know that the internal energy, the differential amount of internal energy is equal to the differential amount of work subtracted by the external pressure times the differential amount of volume. And since we have no transfer of heat, we know that dq here is going to be equal to 0. And we also know that because this is an ideal gas, that the internal pressure is going to be equal to R times T over V. So since this situation is adiabatic, it allows the temperature to change. So this creates a differential amount of temperature in the expression. So now we can use the ideal gas law and the constant volume of times the differential amount of temperature, and we can set this equal to replacing the external pressure with negative R times T over V dV. So now we are going to rearrange this expression by moving some of the variables over. So this will create our CV times differential amount of temperature over T, and that'll be equal to negative R times dV over V. We are now going to integrate on both sides of the expression, from the initial to the final temperature and volume. And we can denote that as T1 to T2 and V1 to V2. So integrating this gives us CV times natural log of T2 over T1, and this is going to be equal to R times natural log of V1 over V2. And we found this by using log rules and flipping this value because of our negative value here. So now we're going to get rid of the natural log by raising both sides of this to E, and this will give us our T2 over T1 raised to the power of CV over R. We just move that over here, and that is equal to V1 over V2. Next, we are going to try to get our expression into terms of our pressure and volume. So we can write this as P1 V1, and we can set this equal to R times T1. And we can go ahead and go P2 V2 equal to R times T2. So now from here, we can go ahead and get some expressions for T1, our first temperature and second temperature. And we get T1 is equal to P1 V1 over R, and T2 is equal to P2 V2 over R. So now, once we get this step, we can plug our T1 and T2 into this expression here. P2 V2 over P1 V1, and this is going to be raised to the CV over R, and this is still going to be equal to volume 1 over volume 2. So when we rearrange this more, we get P2 raised to our specific volume over R times V2 raised to the CV over R, and this is going to be equal to, we're multiplying this over P1 CV over R times V1 times our specific volume over R. And we are going to actually have a +1 in our exponent for our volumes, since we, when we multiply across, we are adding another power of the same volume, so we add that +1. P2 times our specific volume over R V2, and we can make this CV plus R over R equals P1 CV over R times V1 CV plus R over R. So now that we have this, we are going to use the definition of enthalpy in order to denote this expression into a pressure and temperature relationship. So we know that enthalpy is equal to, we can use H for enthalpy, is equal to the internal energy plus the pressure times the volume. And since we know that this is an ideal gas, we can rewrite this as H enthalpy is equal to the internal energy plus R times T. So now what we want to do is differentiate our enthalpy expression with respect to the temperature, and this will give us, we can give dH is equal to dH over dt is equal to d differential amount of internal energy over differential amount of temperature, and this will be plus R. So once we get that plus R in here, we can go ahead and, so from here, we know that the differential of enthalpy with respect to the differential of temperature is going to be our specific pressure. And we know that the differential of our internal energy with respect to the differential of temperature is our specific volume, and this is going to be plus R. So now we are going to use this as a substitution into here to try to derive this further for our pressure and temperature and our pressure and volume relationships. So using this expression, we will get P2 to the CV over R times V2, and CV plus R is equal to CP over R, and this will be equal to P1 CV over R times V1, again using our CP over R. So from here, we're going to raise both sides of our expression to the power of R. And what this will do is pretty much just take the R out of the denominator of the exponent in each expression. And this will give us P2 to the CV times V2 times to the CP is equal to P1 raised to the CV times V1 raised to CP. So now we are going to raise both sides of our expression to the power of 1 over CV. And what this is doing is going to be canceling out some of our exponents and be giving us a ratio in our exponent of CP over CV, which is what we are looking for. So this will give us P2 times V2 to the CP over CV is equal to P1 times V1 to the CP over CV. So now that we are here, we notice that on the left and right side of our equation, we have pressure times volume raised to the ratio of our exponent of our specific pressure over our specific volume. So we can denote this as pressure times volume raised to the CP over CV is constant. And our CP over CV is going to be in the units of gamma or K. Now that we have found the relationship between pressure and volume, we are going to use that to find the relationship between the pressure and temperature in this scenario. So here we have pressure times volume raised to the specific pressure over a specific volume is equal to a constant. So using the ideal gas law, we can write V as volume is equal to R times T over P. So we're going to be moving up here. We can write this as P times RT over P times, or raised to the power of CP over CV is equal to our constant. So now that we have this, we can go ahead and massage this around, and we can get our pressure times, or raised to the power of 1 minus CP over CV, because we have an additional 1 in the denominator, so we are subtracting the 1 that we are multiplying. And then this will be times our temperature raised to the power of CP over CV. And then this again will be equal to our constant. And if you notice down here, we have CP over CV is equal to gamma. So we can replace our CP over CV with gamma in this scenario. So we will get pressure time raised to the power of 1 minus gamma times our temperature raised to gamma is equal to constant. So what we were looking for here is our temperature relationship with pressure. So we will write this as temperature is equal to our constant, and that is equal to our constant times our pressure, and this is going to be times or raised to the power of gamma minus 1 over gamma. And this is going to be our pressure and temperature relationship associated with the adiabatic reversible expansion of an ideal gas.